In the graph domain, deep graph networks often suffer from oversmoothing of node features, limiting their expressive capacity. To address this issue, researchers have explored various upsampling techniques involving node and edge manipulation. However, these methods typically require extensive manual labor and lack a universal integration strategy. To overcome these limitations, we propose UniGAP, a universal and adaptive graph upsampling technique for graph data. UniGAP provides a universal framework for graph upsampling, encompassing most current methods as variants. Moreover, UniGAP serves as a plug-in component that can be seamlessly and adaptively integrated with existing graph neural networks, GNNs, to enhance performance and mitigate the oversmoothing problem. Through extensive experiments, UniGAP demonstrates significant improvements over heuristic data augmentation methods across various datasets and metrics. We analyze how graph structure evolves with UniGAP, identifying key bottlenecks where oversmoothing occurs, and providing insights into how UniGAP addresses this issue. Furthermore, we explore the potential of combining UniGAP with large language models, LLMs, to further improve downstream performance. Our results show that UniGAP can be effectively integrated with LLMs, leading to enhanced performance in graph-related tasks. Overall, UniGAP offers a universal and adaptive solution for graph upsampling, enabling more effective and efficient graph neural network architectures. The authors propose UniGAP, a universal and adaptive graph upsampling approach to mitigate oversmoothing in node classification tasks. UniGAP identifies the critical bottleneck where oversmoothing occurs, providing interpretability to this issue from a graph structure learning perspective. By encompassing various graph upsampling techniques as its variants, UniGAP shows significant improvements over heuristic data augmentation methods, integrating seamlessly with graph neural networks, GNNs, to enhance performance and address oversmoothing. Previous solutions to the oversmoothing problem in GNNs are categorized into three main approaches: manipulating graph topology, refining model structure, and dynamic learning. The authors focus on graph upsampling due to its simplicity and effectiveness, highlighting that previous studies have relied on heuristic strategies that involve significant human effort and lack a universal framework for integration. Graph augmentations aim to enhance model generalization, improve performance, and mitigate oversmoothing. These augmentations are categorized into three main types: node-level, edge-level, and graph-level augmentations. Unlike previous studies, the authors aim to develop a universal framework capable of integrating existing graph augmentations, particularly focusing on graph upsampling, which is designed to be adaptive and optimized without requiring extensive human intervention. The paper introduces key notations used throughout the rest of the paper, focusing on node classification, which involves learning a graph predictor that maps an instance to a label. Key notations include the graph predictor, node attribute feature matrix, adjacency matrix, diagonal degree matrix, and graph Laplacian, providing a foundation for the UniGAP method. UniGAP is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. The framework consists of four main components: trajectory precomputation, multiview condensation, MVC, encoder, adaptive upsampler, and the downstream model. The trajectory precomputation module computes trajectories, denoted as T equals P, G, where T element of RL times N times D represents the trajectories and P denotes the frozen trajectory precomputation module. These trajectories are then processed by the MVC encoder F omega, RL times N times D rightwards arrow from bar right pointing arrow Rn times D to obtain condensed information, denoted as T equals F omega, T. The condensed information T is used to compute the node insertion probabilities between each pair, denoted as P equals U phi, T, where U phi, Rn times N rightwards arrow from bar right pointing arrow re times 1 represents the adaptive UP sampler module. A differentiable upsampling operation S is employed to obtain the augmented graph G equals A, X, equals sulfur monophosphide. Finally, the augmented graph is input into the downstream model D psi for specific tasks, such as node classification. The trajectory computation module is a crucial component of UniGAP, which encompasses multi-view information of each node, including 1-hop, 2-hop, and higher-order information. The trajectories are derived from the output of node features at each layer of the model, implicitly reflecting the gradual process of oversmoothing as the number of layers increases. The trajectories are denoted as T element of RL times N times D, where L represents the number of layers, N denotes the number of nodes, and D signifies the dimensionality of features. The representation of each hop is denoted as H, L, equals F, L, H, L minus 1, element of Rn times D, where F, L, means the LTH layer in the trajectory computation model. A channel-wise L2 normalization, norm, Xi, equals Xi, 2, is employed to regulate the magnitude of features that may escalate exponentially with the number of iterations. To obtain initialized trajectories, 3 off-the-shelf strategies are explored: zero initialization, nonparametric message passing, and pre-trained GNN. These strategies are integrated into the UniGAP method to obtain initialized trajectories. The framework is designed to be flexible and adaptable, allowing for different trajectory precomputation strategies to be employed. The framework is also designed to be efficient, with the trajectory precomputation module only needing to be performed once in each task. The MVC encoder, adaptive upsampler, and downstream model are CO trained to obtain the optimal graph structure. Graph neural networks, GNNs, often suffer from the oversmoothing problem, which arises from the repeated application of message passing and feature transformation. To address this limitation, the authors propose a novel approach, introducing the UniGAP module, which adaptively updates the graph structure during training. The UniGAP module consists of 3 key components: trajectory generation, multiview condensation, and adaptive graph upsampler. Trajectory generation involves 3 methods to create node trajectories, capturing multiview information. The first method, zero initialization, initializes trajectories with zeros, ensuring minimal noise and tailored graph structure learning for each downstream task. Nonparametric message passing decouples message passing and feature transformation, preserving original feature and graph topology information. The third method, pre-trained GNN, leverages a pre-trained GNN model to obtain a generalized feature extractor, initializing encoding parameters in the downstream model. Multiview condensation adaptively condenses multiview information into compact features reflecting nodes' propensity to oversmoothing. 2 strategies are proposed to instantiate the multiview condensation encoder: trajectory MLP mixer, TMM, and trajectory transformer, TT. TMM applies trajectory mixing and channel mixing to obtain condensed multiview features, while TT treats each hop feature as input tokens, using a transformer encoder to learn mixed hop representations. The adaptive graph upsampler uses condensed trajectory features to compute upsampling probability for each existing edge, mitigating oversmoothing. Upsampling logits are computed using a differentiable sampling method, and the Gumbel softmax trick is employed to derive the upsampling mask and generate the augmented graph. Mathematical formulations for each component are provided, including zero initialization, nonparametric message passing, pre-trained GNN, and multiview condensation. By adaptively updating the graph structure during training, the UniGAP module can mitigate oversmoothing and improve GNN performance on various downstream tasks. However, limitations include potential computational costs of the pre-trained GNN method and the need for careful hyperparameter tuning. Future work may involve exploring alternative trajectory generation and multiview condensation methods, as well as applying the UniGAP module to various GNN architectures and downstream tasks. UniGAP is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. The methodology centers around a novel edge selection method based on highest probabilities, ensuring differentiability and maintaining the gradient equal to the soft gradient. This approach achieves 2 primary objectives: producing exactly 1 hot output and maintaining the gradient equal to the soft gradient. During model training, the augmented graph is fed into a downstream model to compute the downstream loss, which is then combined with oversmoothing metrics, such as mean average distance, MAD, and Dirichlet energy, as regularization terms. The total loss is defined as the sum of the downstream loss and the regularization term, and the model is trained in an end-to-end manner through backpropagation. UniGAP's universality allows it to be integrated with various graph neural network (GNN) models, encompassing most existing graph upsampling techniques. By combining different components and strategies, UniGAP can be considered as variants of existing techniques, such as half-hop, ADA-edge, and graph mix-up. Theoretical explanations provided in the paper demonstrate how UniGAP learns in concert with downstream tasks to obtain the optimal upsampling graph structure, effectively mitigating the oversmoothing problem. A closed-form solution is presented, showcasing UniGAP's ability to adaptively change the node's receptive field and learn the message passing dynamics. By optimizing the joint loss of the downstream model and UniGAP, the approach learns the optimal structural representation for downstream tasks. The UniGAP approach is explored in this section, focusing on its ability to slow down the smoothing rate of node feature covariance during message passing. A theoretical analysis, supported by lemmas and a theorem, demonstrates the effectiveness of UniGAP in reducing oversmoothing. Lemma 3.2 approximates the risk after k rounds of message passing in the original MP model as R, k, approximately equals reg a squared k sigma, where a equals I plus sigma caret 1. This reveals that the original MP model's smoothing rate is 2k due to the a squared k sigma operator. In contrast, Lemma 3.3 presents the approximated risk with UniGAP, R, k, underscore UniGAP approximately equals reg a caret, k1, I plus 1p, I plus pa, squared, sigma, where p equals e, p, 0, and p denotes the upsampling probability at the optimal graph structure. The authors show that the smoothing rate of MP with UniGAP is k1, roughly half the rate of the original MP model. Theorem 3.4, slower smoothing of UniGAP, formalizes the result, stating that the risk obtained with UniGAP after k rounds of message passing is R, k, underscore UniGAP proportional a caret, k1, which is roughly half the rate of smoothing compared to the original MP model's R, k, proportional a squared k. This theoretical analysis demonstrates that UniGAP effectively reduces the smoothing rate of node feature covariance during message passing. A complexity analysis of UniGAP reveals that its time complexity is O, lane plus L plus lane squared, comparable to traditional layer GNNs, and its space complexity is O, E plus LD squared plus lane squared, similar to that of traditional GNNs. The experimental section presents a comprehensive empirical investigation, addressing 5 research questions. UniGAP is evaluated on 8 node classification benchmark datasets, comprising 4 homophilic and 4 heterophilic datasets. It is compared with various baseline models, including traditional GNN methods, advanced GNN methods, and graph transformer methods. The results demonstrate that UniGAP significantly enhances traditional GNN models on heterophilic datasets, with average absolute improvements ranging from 5.0% to 13.3%. UniGAP also outperforms other graph upsampling methods, such as half-hop, with an absolute improvement of over 3.9% on GCN. On homophilic datasets, traditional GNN models benefit from their inductive bias, but UniGAP can still identify graph structures that enhance downstream tasks through adaptive graph upsampling. Node classification performance on homophilic and heterophilic graphs is presented in Table 1, showcasing the results of various graph neural networks with and without UniGAP. The table highlights the consistent improvement of UniGAP across different datasets, with average absolute improvements ranging from 1.1% to 4.8% compared to baselines including GCN, GAT, GraphSage, GCNII, GGCN, H2GCN, and GPR-GNN. Notably, UniGAP demonstrates a significant improvement, with an average absolute boost ranging from 1.4% to 6.7%, surpassing state-of-the-art baselines. This underscores the effectiveness of UniGAP in mitigating oversmoothing in node classification tasks. To further analyze the extent of UniGAP's mitigation of oversmoothing, experiments were conducted on GCN across several datasets, evaluating its accuracy and mean absolute difference (MAD) as the number of layers increases. The results show that UniGAP significantly enhances model performance and alleviates oversmoothing at each layer, surpassing ADA edge and half-hop. In terms of interpretability, the ratio of intermediate node insertions is examined to better understand the reasons for mitigating oversmoothing. The analysis reveals that new nodes tend to be inserted between interclass node pairs, slowing down message passing between different classes and preventing features from collapsing into identical vectors. This mitigates the oversmoothing problem. Additionally, some intraclass edges containing noise are eliminated, improving performance. Overall, the results demonstrate the effectiveness of UniGAP in improving node classification performance and mitigating oversmoothing in graph neural networks. The authors of the research paper assess the performance of their proposed UniGAP methodology across various datasets and compare it with other upsampling methods. They also conduct an ablation study to understand the impact of different strategies within the UniGAP modules on model performance. Firstly, they compare the accuracy and mean absolute difference (MAD) values of various upsampling methods in different layers on the core dataset. UniGAP consistently outperforms other methods, demonstrating its effectiveness in alleviating the oversmoothing issue in graph neural networks. In the ablation study, the authors explore three strategies for instantiating the trajectory precomputation module: zero initialization, nonparametric message passing, and pre-trained GNN. Pre-trained GNN consistently outperforms both zero initialization and nonparametric message passing, likely due to its ability to learn unique information from the graph. The authors also compare different strategies for the multiview contrastive (MVC) encoder, including no encoder, trajectory MLP mixer (TMM), and trajectory transformer (TT). Both TMM and TT demonstrate significant improvements compared to not using an MVC encoder, with absolute improvements ranging from 1% to 1.92%. Additionally, the MVC encoder effectively compresses the trajectory features, reducing the time consumption for subsequent processes. Furthermore, the authors compared different initialization strategies for inserted nodes, including zero initialization, mean feature of source and target node, and learnable weighted sum of source and target node features. The learnable weighted sum achieves the best performance because it can adaptively adjust the weights of source and target features, thus generating better inserted node features. Finally, the authors explore the potential of combining UniGAP with large language models, LLMs, on text-attributed graphs. UniGAP consistently enhances downstream performance when combined with LLM features, likely due to the improved quality of node features that enables UniGAP to identify a better upsampled graph. UniGAP is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. By integrating various graph upsampling techniques, UniGAP enhances the adaptability, performance, and interpretability of graph neural networks, GNNs. The authors demonstrate the potential of combining UniGAP with large language models, LLMs, such as Llama 27B, to generate hidden features that improve node classification performance. Oversmoothing in GNNs occurs when the features of nodes in a graph become increasingly similar during the message passing process, leading to poor classification performance. Existing solutions, including graph upsampling techniques, have limitations. UniGAP addresses these limitations by preserving the local structure of a graph while reducing oversmoothing. This approach adapts to different graph structures and node features, making it a versatile tool for various graph-based machine learning tasks. The authors evaluate UniGAP on benchmark datasets, such as Archive and WikiCS, and demonstrate its effectiveness in improving node classification performance. The results show that UniGAP consistently outperforms existing graph upsampling techniques and achieves competitive performance with LLMs. When combined with Llama 27B, UniGAP generates hidden features that significantly improve node classification performance. The paper provides a comprehensive analysis of UniGAP's performance, comparing it to state-of-the-art methods. The results indicate that UniGAP provides a robust foundation for future research in this area, offering valuable insights and practical solutions to long-standing challenges in graph neural networks. The authors discuss future work, including more intricate combinations of UniGAP with LLMs and further advancements in graph upsampling. UniGAP is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. The authors evaluate UniGAP on 8 node classification benchmark datasets, consisting of 4 homophilic and 4 heterophilic datasets, with publicly accessible train validation test splits. Homophily is measured using the homophily metric suggested by 26. The datasets include citation networks such as PubMed, CiteSeer, and Quora, where vertices represent scholarly papers and adjacency is established through bibliographic citations. Vertex attributes are represented as bag-of-words representations of the related manuscript, with vertex categorization reflecting the scholarly domain of the associated paper. Other datasets used include AugBNarchive, a directed graph representing the citation network among computer science archive manuscripts, and datasets from the WebKB corpus, such as Texas, Cornell, and Wisconsin, where vertices correspond to web pages and adjacency is based on hyperlinks. The actor dataset is a subgraph of a larger network of film directors, actors, and screenwriters collated from Wikipedia entries. Experimental results are reported for various hyperparameter settings, including learning rate, hidden dimension, dropout, weight decay, activation function, and layer number, which are chosen to achieve the highest performance on the validation set. For GCNII, additional hyperparameters alpha and theta are considered, while for UniGAP, MVC dimension and weight are tuned. For half-hop, P and alpha are hyperparameters. The paper provides theoretical proofs, building upon the work of 22, and relies heavily on the lemmas and proofs in the original paper. Specifically, the proof of proposition 3.1 is presented, which considers a simplified situation of linear GNN with mean aggregation. The smoothed node features after k rounds of mean aggregation are derived, and the regression coefficients vector on the smoothed features is obtained for a single mean square error loss and ridge regularization. Graph neural networks, GNNs, rely on optimal graph structure to excel in downstream tasks. To achieve this, Wang et al. Present UniGAP, a method for learning the optimal graph structure for GNNs, specifically for message passing. Their approach approximates the optimal message passing parameter, k, allowing GNNs to operate on the optimal graph structure. The authors start by defining test risk, R, k, which measures the GNN's performance on unseen data as the mean squared error between predicted and actual values. An optimal k operator, is known to minimize this risk. To find the optimal graph structure, they propose an optimization objective combining learnable GNN model parameters and the optimal upsampling matrix, theta and theta u respectively. Deriving update rules for theta and theta u from the Lagrangian forms derivatives with respect to theta and theta u and setting them to 0, yields the optimal solutions. This approach determines the learnable parameters and the upsampling matrix that constitute the optimal graph structure. Wang et al. Then examine lemma 3's proof, employing the latent space random graph model and case steps of smoothing regression risk. By comparing UniGAP's insertion of new nodes in the graph, the rate of smoothing for the original message passing, MP, algorithm is identified as 2k. Then, UniGAP's regression risk, reflecting this new transformation to the MP process, can be deduced. A derivation from the results and with optimal message passing step can ultimately account for an augment and novel efficient handling is augment smoothing augment incorporating optimization applied derivation confirm UniGAP improving approach. This helps explaining improvements, task-specific enhancements, thereby applied such cases exploiting deep feature acquisition, supporting our efforts over significant complexity, especially relative best real with efficacy tested handling, enhancing techniques, modeling, enabling enhancements, advanced developments, architectures, knowledge, existing design aspects, combined multiple, achieving remarkable as is various challenging, demonstrating support domain, showing augmentation impacts, impact capabilities, several developing, building stronger progress, multiple, many relevant, even surpasses, improvement confirmed when coupled, developed, confirmed methodologies, testing demonstrates, supports, action date. The UniGAP algorithm is a universal and adaptive graph upsampling approach designed to mitigate oversmoothing in node classification tasks. It consists of 5 key functions: trajectory precomputation, MVC encoder, adaptive upsampler, downstream model, and main. The trajectory precomputation function computes initial trajectories from the input graph G. These trajectories are then processed by the MVC encoder function, which utilizes a multiview condensation encoder with parameters omega to output condensed trajectories T. The adaptive upsampler function computes upsampling probabilities and applies them to the condensed trajectories, generating an upsampled graph G. This process employs Gumbel's softmax to ensure differentiability. The downstream model function trains a model on the upsampled graph G, using parameters psi, and computes the loss. The model parameters are iteratively updated to minimize this loss. The main function orchestrates the entire process, starting with trajectory precomputation, followed by multiple rounds of encoder, UP sampler, and downstream model operations. The optimized model is returned as the output. The mathematical equations provided elucidate the message passing process within the UniGAP algorithm, demonstrating how node features are updated and how the algorithm mitigates oversmoothing. The UniGAP algorithm's pseudocode identity is established, highlighting the practical implementation of this novel approach. By leveraging the UniGAP algorithm, researchers can effectively address the issue of oversmoothing in node classification tasks, leading to improved model performance and accuracy.